Good day, everyone. Welcome to my video on complex numbers and applications. And hopefully these will be applications you find interesting. Well, before we define exactly what a complex number is, let's recall numbers we're familiar with, real numbers. And we can visualize a real number as being a point on the real number line. For example, the number 3. So here I have a picture of what's known as the real number line. And our interpretation of the number 3 is you have an origin right here, and you take 3 steps to the right, 1, 2, 3, there you are. So all real numbers can be represented as points on this line. Now, then something happens where we run into an equation like this that we need to solve. X squared plus 1 equal to 0. And when solving that, we're going to get x equal to plus minus square root negative 1. And we recognize that there's no real number that you can square and get negative 1. So this has no real solution. Thus, we invent a number called I, I, which we can refer to as the imaginary unit. It's an imaginary number. And thus we invent this number, square root negative 1, and we call it I. Thus, I squared would be equal to negative 1. Okay, so these are imaginary numbers. For example, if I have the square root of negative 4, and using the properties of square roots, that can be written as the square root of 4 times square root negative 1, that would be 2i. So what we're going to do is, since these imaginary numbers don't fall on the real axis, we introduce a new axis here called the imaginary axis. And here, the number I would land right here. There's I. So all my imaginary numbers would be points on this axis here. 2i would be right here. Here, that's 2i. And again, over here is the real number 3. Now, when I do this, when I let this axis represent real numbers and this axis represent imaginary numbers, we have created something that's referred to as the complex plane. C. So here we have the complex plane. Because there's other points in this plane that don't fall either on the real or the imaginary axis. For example, this point right here. And that point right there would be a geometric representation of what we call a complex number. So now let us define what we mean by a complex number. Complex number will have this form. We use the variable z for complex numbers, and it could be written as a plus b times I. And here, so a is understood to be the real part of the number. So this is the real part. And b, not b times I, but b itself is what we call the imaginary part. So a complex number has a real part and an imaginary part. And it corresponds to a point in the complex plane. For example, if you have the number z equal to 3 plus 2i, and you want to find that number in the complex plane. Well, you take 3 steps in this direction on the real axis, and we can think of I as meaning I tells us to rotate 90 degrees. So we take 3 steps, rotate counterclockwise 90 degrees, and take 2 steps, and there you are, 3 plus 2i. Another example of finding a complex number, suppose I have -1 plus I. For this number, we would take 1 step in this direction, -1, go up 1 step in this direction, and there's the number -1 plus I. Well, complex numbers have something called next thing I want to do is to find something called the complex conjugate. So if I take a complex number and I write this little star here, this superscript, that's called the complex conjugate of the complex number. How do we find the complex conjugate? Well, if z is equal to a plus bi, the complex conjugate is found this way. It's a, but the imaginary part you take the opposite of. Here we go. So some examples over here, if I have 2 plus 3i, the complex conjugate would be 2 minus 3i. Looking at some other examples of computing complex conjugates, we'll make this little table here. So here if I have z is -1 plus I, our complex conjugate is you don't change the real part, but whatever you see here, you take the negative of. So that's -1 minus I. If you have a pure imaginary number like, let's say 3i, the complex conjugate is minus 3i. And then, of course, if you have 2 minus I, the complex conjugate would be 2 plus I. Now also, we could talk about, when we're dealing with a complex number, and let's draw another complex plane over here real quickly. So this is the real axis. This is our imaginary axis again. Now if I have this complex number right here, z, we can refer to the magnitude of a complex number. So this is the notation for the magnitude of z. It's a real number. And what it is, it's the distance that that number is to the origin. So this number right here happens to be a plus bi, meaning that the real part is a and the imaginary part is b. We can construct a triangle to see what the magnitude of that complex number is. It will be the hypotenuse of that triangle. So, if z is a plus bi, the magnitude of z is equal to a squared plus b squared square root. So an example of computing the magnitude of a number, if I have 1 plus 2i, the magnitude of this complex number would be 1 squared plus 2 squared, square root, it would be square root of 5. So complex numbers have magnitudes. Now, back to the complex conjugate. If I do this notation here, the R with this little subscript E, that means the real part. So the real part of A plus BI, that's equal to A. The imaginary part, we write like this, and the imaginary part of A plus BI, it's not BI. The imaginary part is B. And notice this, if you take a number, complex, and add it to its conjugate, and divide by 2. Well, to do that, we have to tell you how to add complex numbers. Well, let's see what we get. It's A plus BI plus A minus BI. So how do I add these two complex numbers? To add complex numbers, the real parts add, which gives me 2A, and the imaginary parts add, which cancel out. So here, the real part of a complex number can be found by adding the number to its conjugate and dividing by 2. And that gives you the real part of Z. So we want to look a little bit more detail into doing operations with complex numbers. All right. And do that on the next sheet. Operations. Well, again, to add two complex numbers, and we'll give you an example, 2 plus I, and I want to add that to 1 plus 3I. And the result down here is the real parts add, which is 3, and the imaginary part is 4I. But we want to interpret exactly what we're doing. What are we doing when we're adding two complex numbers? Well, let's take a look at it over here on the complex plane. Real axis, imaginary axis, complex plane. So, first of all, if I'm adding just real numbers, like if I'm taking 3 plus 2, and I want to kind of visualize this operation on the real number line, what you would do is you would say, okay, 3, take 3 steps, 1, 2, 3, and you land here. And then it says take 2 more steps, 1, 2, and you land here, and your result is 5. Well, for adding complex numbers, I'm going to take 2 in the real direction, 1, 2, plus I, which brings me right there. And then after that, I'm going to take 1 plus 3I, which says go in the real direction 1 unit and go up 1, 2, 3, and we end up right here. Right there. And that number right there has a real part of 3. So where do we land? 1, 2, 3, 1, 2, 3, 4. And so we are at 3 plus 4I. Adding those two numbers. Now, to multiply complex numbers, let's use those two numbers. 2 plus I times 1 plus 3I. To multiply these two complex numbers, we're going to do it in a similar way that we would multiply binomials in algebra. You might recall that when you do that, you have this little memory aid, FOIL. So we take the first two and multiply them by each other, which gives us 2. I'm going to take the outer, which is 2 times 3I, which gives me 6I. I'll take the inner, which is plus I, and then the last terms is I squared. It's 3I squared, and I squared is -1, so it's minus 3. Now combining the real parts, I have 2 minus 3, so it's minus 1, and my imaginary part is plus 7I. Let's take a look at that on our calculator and confirm that result. On the TI-84 calculator, you can access I. It's a second function key. Decimal point will give you I. So here I have 2 plus I times 1 plus 3I, and evaluate it, I get minus 1 plus 7I. Same answer. When we carried out this multiplication, we noticed that the real part of our result came from the first and the last terms. That will always happen. When I multiply two complex numbers, I'm going to get a real part and I'm going to get an imaginary part. The real part came from multiplying the first terms and the last terms. You're always going to have that I squared, which is going to be turned into a real number. So sometimes it's better to do it in this order. Take the first terms and then multiply by the last terms. Now the outer and inner are what yields the imaginary part. So this is FOIL, but for complex numbers, we like FLOI. Take the first and last. Now, why this is useful is oftentimes when we're multiplying complex numbers, we might just want the real part. We might be doing an operation where we just want the real part of the answer. Or we might be doing an operation where we just want the imaginary part of the answer. So if we just want the real part of the answer, we know, hey, just take the first and the last. So let's redo this, doing FLOI. The first is 2 times 1, which is going to be 2. And then I have I squared minus 3, which is minus 3. So this is my first and last. Now the outer is 6I, and the inner is I. And of course we're going to get the same result. 2 minus 3 is minus 1 plus 7I. Now, what we would like to do is interpret exactly what is going on. What's the intuition behind multiplying two complex numbers? Well, first thing we notice is that when you multiply two complex numbers, your result is a complex number. And so what's going on here? Well, we're going to get to that in a moment. But before we do that, we want to look at division. So as an example, we're going to take 2 plus I and divided by 1 plus 3i. Dividing two complex numbers. Now, we might give you this ratio right here. We might ask you, hey, what is the real part of this? What is the real, hey, I take a complex number and I divide it by a complex number, I have a complex number which has some real part. And we ask, what is the real part? Well, you can't answer that until you carry out the division and put it in the standard form. It has to be in the form a plus bi, where you can then see what the real part is. Now, the way we're going to carry out this division is as follows. We're going to multiply the top and bottom by the complex conjugate of the denominator. Okay? Okay. Hey, I want to change my problem here. I meant to put 1 minus 3i here. 1 minus 3i, which is going to change this to a plus and a plus. Okay, so we're taking 2 plus I and we're dividing it by 1 minus 3i. Okay, and now, why are we multiplying the top and bottom by a complex conjugate? Well, over here as an aside, there's something really special that happens when you multiply a number by its complex conjugate. Let's see what happens. We'll take this number, multiply it by its complex conjugate. Well, I can look at this as a difference of two squares, a plus something, a minus something. That's a squared minus bi squared, but I squared is -1. That's a squared plus b squared. So two special things happen when you multiply a number by its complex conjugate. Your answer is real. And not only that, your answer is the magnitude of the number squared. So it's going to be the magnitude squared. Thus, let's look at this. So my denominator here, 1 minus 3i, 1 plus 3i, it's going to be 1 squared plus 3 squared. It's 10. The magnitude of that number is square root of 10. And then the top, well, we've already done that multiplication up here. We'll go ahead and put that result down. It's -1 plus 7i. So the result of this division is -1/10 plus 7/10 times I. Let's check that with our calculator. There we go, 2 plus I divided by 1 minus 3i. And we get -1/10 plus 7i. Same answer. Okay, so now that's pretty much it with the operations, adding, multiplying complex numbers. But we want to delve into exactly what is going on here when you're multiplying complex numbers. And to do that, we are going to introduce polar form of a complex number. So here, showing our complex plane, if I have this complex number right there, right here it is, z, which happens to be 3 plus 2i, we know the magnitude of z is the distance to the origin, and often we like to use this little abbreviation for the magnitude of some complex number. We like to use the letter r, which would stand for like radial. It's the radial distance. But a complex number not only has a magnitude, is if you drew a line connecting that number to the origin, that line is going to form some angle, which we'll call theta, with the real axis. So this complex number can be completely described by its magnitude and the angle that this line makes with the real axis. And so the polar form would be as follows. It would be some magnitude, and now we've got to somehow indicate the angle. One way of doing it is using this little angle bracket, r at theta. So that's our first crack at giving a polar form for a complex number. So in other words, if I say the number is 5 at an angle of 30 degrees, and this form, and we're going to modify this shortly, 5 at 30 degrees, it's pointing to the same point in the complex plane. It's saying go out 5 units and rotate 30 degrees. So when you have a complex number in this form, you're using these polar coordinates. You're using what the magnitude is of the angle. And hey, if I ask what the real part of this is, if you want to go back to this form, which is called rectangular. Okay. So let's first show how, if I have this form, I could go this way. Well, we could construct a triangle here for a moment. And if this is A, and this is B, and this is the magnitude of the complex number, which I'm using the letter R for, and this is the angle theta, we notice that from trigonometry that the cosine of theta is going to be A over R. So A is equal to R cosine theta. And B is R sine theta. So if I had this complex number, square root of 2 at 45 degrees, well, we could convert that to rectangular form without using any of this because we would recognize what this looks like. Because we know that if I go over 1 and up 1, this is going to be square root of 2. So this is going to be 1 plus I. So my complex number written in terms of these polar coordinates could be written this way. R cosine theta plus R sine theta, which is B times I. So here I've written my complex number, but I'm using the polar coordinates. Now, we might notice that we could also write this as R. I could factor out the R as cosine theta. Now, this is done. This I, which is written here, we can put it before the sign. So there's my complex number. Now, then if we recall Euler's identity, which says e to the I theta. So this is a complex exponential. That's equal to cosine theta plus I sine theta, and we recognize that. So here is our representation of a complex number in polar form. It's z is equal to r e to the I theta. Okay. That's our polar form. Now, if you have square root of 2 times e to the I 45 degrees, that should be the same as 1 plus I. Let's demonstrate that on a calculator. So on our TI-84, if we go to mode, and when we're dealing with complex numbers, we can make our default representation, and let's zoom in here. We can say, hey, I want my default representation to be rectangular form, or notice this, r e to the I theta, polar form. So I'm going to go over here and change my default representation to polar form. And I'm going to put in the number 1 plus 1 plus I. I'm going to change my mode to degrees. Let's try it. 1 plus I. And hit enter. It's going to come back with square root of 2, which is 1.41, e to the 45 degrees. Now, we could have done it this way. We hit math, we go to math and go over to complex. See all the things we could do with a complex number. We could extract a conjugate, real part, or I can convert into rectangular or convert into polar. So if I do it this way, 1 plus I and say go to polar, let's see what we get. That. With that, we can now interpret what's going on when you multiply two complex numbers. Suppose I have a number, complex number R1, e to the I theta 1. I'm going to take that and multiply it by some second complex number, well, when your complex numbers are in polar form, the multiplication is trivial. The magnitudes will just multiply. That's going to be equal to R1 times R2, and the angles will add. So when you're multiplying a complex number by another complex number, you think if you're operating on this number, what you're doing is you're changing its magnitude and changing its angle. Magnitudes multiply, the angles add. So if I take the I and I multiply it by 1 plus I, we're just carrying out this multiplication. That's going to be equal to I plus I squared, which is minus 1 plus I. Okay? Well, so what happened here? This I, the magnitude of this is 1, so this is e to the I 90 degrees. I has a magnitude of 1, the angle is 90 degrees, and so when you're multiplying by I, you're just saying rotate this 90 degrees. This right here was root 2 e to the I 45 degrees. So what we should have ended up with, the magnitude didn't change, that's square root of 2, but e to the I 135 degrees. Let's visualize that real quickly here. So if we go over here, looking on the screen, we're looking at GeoGebra, and I've defined this complex number z1, which is 1 plus I. Now, I'm going to construct a circle which will have a radius of square root of 2, because that's what the magnitude of z1 is. Now let me do some operations on z1. If I take 2 times z1, I get this new number, z2. But here, since I just took z1 and multiplied it by a real number, all I did was change the magnitude. It's got the same angle. Okay? It has the same angle. Now, if instead I took I and multiplied it by z1, what that did was it took z1 and rotates it 90 degrees. So there's my result. That's now z3. And so it has the same, so the operation that we did was we took z1 and just multiplied it by I. It didn't change the magnitude. It just rotated it in the complex plane by 90 degrees. Now, if we take z1 and multiply it by z1, the result's going to be, let's try this, z1 times z1. Well, the polar representation of this number is a square root of 2 at 45 degrees. So 45 plus 45 is 90. You're going to land right over here. All right. We'll go back to here to see what happened with that problem. We took 1 plus I and multiplied by 1 plus I. Well, this number right here is a square root of 2 at 45 degrees. So say, take this, when you multiply this by this number, it says, take this number, multiply the magnitude by the square root of 2, and rotate it 45 degrees. Well, this happens to be the same number. And the result is going to be 2 at an angle of 90 degrees, which is 2I. So thus we have we could kind of encode a rotation in the plane, that is. We can encode a rotation in a complex number. And 1 plus I, final thing here, multiplying these out by doing FLOI, the first would be 1, the last will be I squared, which is minus 1. First, last, the outer will be I, and the inner will be I. And so, as we suspected, it is 2I.